Hi, I'm Lily, and this is Phil. And today we're going to talk about quantum tunneling. Classical tunneling is when something digs underground.
And quantum tunneling is when subatomic particles do it.
Not quite. Quantum tunneling is when a particle, usually an electron, doesn't have enough energy to go around or through a barrier, but it still ends up on the other side.
Spooky.
Two important aspects in understanding quantum tunneling is particle-wave duality, meaning that particles act like particles, but also waves, and the uncertainty principle.
You mean like how I'm uncertain about what's going on?
No, the principle more states that the more you know in a particle's velocity, the higher probability you'll have in its position, and vice versa. These two concepts help to explain quantum tunneling, and we can use an example of, say, throw something in the air. Take Phil. Okay, we'll use a ball. If you throw a ball into the air, we know from classical physics that the ball can be anywhere from the ground to its maximum height, but it'll never be at a height greater than its maximum height. Now say the ball is a particle. Because of the fact that at the top of the arch, the velocity of the particle is pretty well known to be zero, and that particles can act like waves, we know that there's a higher probability in the particle's position. And there is a possibility that the particle could be at a height greater than its maximum height.
So if you really want a thrill, ride one of those slingshot rides a quantum theme park?
That definitely would be interesting. If we look at this diagram, that is, say, a particle coming up on a barrier, you can see that on this side of the barrier, the probability of the particle being at the position is pretty high. But as it hits the barrier, the probability of the particle being at this position drops down. But if the barrier is thin enough, or the particle has enough energy, even though it's a lot less, you can see that there's still a probability that the particle could end up on the other side of the barrier.
Okay, but I thought you said the particle doesn't have enough energy to go through the barrier.
That's the thing, they don't. Tunneling's a bit of a misleading name. It's more of the particles kind of pretending the barrier doesn't exist.
You mean like the kids did you in high school?
Moving on. And it's proven that the particles just kind of pass over the barrier because scientists can measure the amount of energy the particle has before and after the barrier, and guess what?
What?
They're the same. If the particle was actually tunneling through the barrier, some of its energy would have been lost.
This is cool and all, but how can particles moving past a barrier be of any real use?
Actually, quantum tunneling is very useful. One important use is a scanning tunneling microscope that can look at things on the atomic level. It can be used in a vacuum, water, or air, and in freezing or really hot temperatures. The microscope uses a conducting tip that gets very close to the surface, and electrons tunnel through that space in order to produce the image. Quantum tunneling is also used in tunneling diodes, which are electric semiconductor devices, and in nuclear fusion in stars.
Wow, I wonder if I could be that useful if I learned to tunnel.
Probably not, but quantum tunneling is very useful in physics, and it's a very amazing phenomenon.